Hi, we're Lab Group 6B, and this is Lab 5, Spherical Aberration. I'm Ridley, and in this lab I helped with the alignment of the microscope and data taking.
I'm Daniel Moore, and this lab I helped with optomechanics and knob turning.
I'm Cameryn, and I helped with optical alignment and data taking.
The objective of this lab was to experiment with spherical aberration and shape factor. Specifically in this lab, we measured transverse and longitudinal spherical aberration of a plano-convex lens.
Spherical aberration causes the power of the focal length of the system to vary with pupil radius. From the diagram, you can see that the marginal focus will come to focus much closer than the paraxial focus. The difference between these two locations is the longitudinal spherical aberration. As we progress through the lab, we align the microscope to the marginal focus position when measuring the transverse ray aberration, and then we move to the paraxial focus to measure the longitudinal ray aberration. In the graph shown, we can see how the transverse spherical aberration changes with respect to shape factor. For our purposes, we use a conjugate factor of -1 because we were imaging an object at infinity. We can see that when the shape factor is equal to -1, we get much worse aberration than if the shape factor was equal to 1. We also calculated the optimum shape factor for this configuration to be 0.7143. So here we have two graphs and images for different shape factors. So we can visually see that the rays come to focus at a much tighter spot when B is equal to 1. And then on the ray fan plots, we can also compare the scales. So for when B is equal to -1, we can see the scale is plus or minus 2,000 microns, where when B is equal to 1, the scale is only plus or minus 500 microns. So there's definitely a big difference in the amount of spherical aberration present.
The numerical aperture of the microscope objective is important to take into consideration because if we choose a numerical aperture that's too small, the light we want to measure might be vignetted. Because of this, we calculated the numerical aperture of our test lens to be 0.127. To make sure that all the light from this lens is used in the experiment, we need a numerical aperture that is equal to this or larger. In this case, we chose 0.25 to capture all the light coming from our lens, but also give us a little bit of wiggle room, while also preventing the beam from expanding extremely rapidly like higher numerical aperture objectives will do.
Here we have images of our setup. We have the Heaney laser incident on a pentaprism, which deviates the beam 90 degrees onto the next rail. On this rail, we have the Hartmann mask, followed by a 100 millimeter focal length test lens, followed by the microscope. We align the microscope objective similarly to how we did in Lab 1. We adjusted the tip and tilt and translation of the microscope. We knew it was aligned when the new beam and the crosshairs were aligned with the original beam. This is our beam after alignment through the microscope. We began by measuring transverse spherical aberration by moving the pentaprism along its rail such that the laser beam scans across the transverse direction of the Hartmann mask. With the laser going through the most extreme hole on either side of the mask, we measured the distance the beam moved from its initial position as a result of the laser line now entering the edge of the lens with a ruler. We did this across the full width of the Hartmann mask and took measurements at each individual hole on the mask. These are our results taken in lab, and from this we see that the transverse ray aberration does follow the known equations and what we would expect. We did this both when the lens was positioned for maximum spherical aberration and when the lens was positioned for minimum spherical aberration, which we can see in our data. We took these measurements on the wall, and as we scanned across the beam, we saw that the beam goes out and then back in for marginal focus as it approaches paraxial focus.
We again measured transverse spherical aberration, but this time instead of measuring the spot change on the wall, we measured the spot change by taking the displacement of the microscope, by using a translation stage on the translator microscope in the x direction across the rail. So from our second run of measuring transverse aberrations, this was the data we collected. As you can see, when compared to the Zmax calculations, our magnitude is much, much greater. And this is mostly likely due to the defocus that we have in our system. Now we measured longitudinal spherical aberration by scanning the beam across the Hartmann mask and translating the microscope along the optical axis to find the location when the spot is then again centered on the target. The longitudinal spherical aberration is the difference between the paraxial image and marginal image locations. The plot on the left shows the measurements we took in lab. As you can see, our data very closely matches the behavior we expect to see.
Unfortunately, in lab, we ran out of time to test a biconvex lens, but we wanted to take a moment to talk about it. The shape factor of a biconvex lens is 0. Theoretically, it works best with one-to-one imaging, and it isn't the most suitable option when objects are infinity or as a collimating lens, but as the graph shown at the beginning of this video, it isn't necessarily the worst option.